So if you haven't met me yet, my name's Mathis, and this is a project that I've been working on for a couple of years. This is not AbGradCon, sorry, that's embarrassing. So yeah, emergence of life as a first order phase transition. So to preface this a little bit, give you guys a bit of an explanation of what's going on here. This is completely different than everything else I've seen here. So in evolutionary biology and mathematical biology, you see these replicator models every once in a while. And these are a sort of abstraction to help understand biological evolution in terms of variation and selection and replication. And so these models are really interesting, but I'm more interested in how what we call chemical evolution eventually became biological evolution. And so for this particular project, I focused in on one function that seems to be really important to biology, and that's replication. And if you think replication isn't necessary for biology or evolution, I might agree with you, depends on the day, and I'd love to have that conversation, so find me after. But what I became interested in is, in normal replicator models, they sort of have, replicators exist as a given. And so what I wanted to say is, okay, what if they just don't exist as a given? They have to be made sort of from some underlying chemistry that ultimately constrains their ability to replicate and evolve. So I'm going to describe a model and some results that I have. So cool. So the chemistry that I described, it's really simple. It's not even really chemistry, but there's these two elements. Here they're purple and blue, 1 or 0, however you want to think of them. These can come together and add 1 to the end to form sequences through polymerization. And any sequence can degrade at any point and break into smaller pieces. And if you get above a certain length, in this case I said length 7, you can make a copy of yourself, and you're constrained by what resources are available. It's a closed mass system, so there's always the same number of blue and purple squares. It's not closed energy. If you're into rate equations, I can show you why afterwards, but there's definitely an energy flux going on. And replication is perfect. There's no mutation, so there's no novelty introduced via replication. The only novelty is through polymerizing new sequences. And this might look a little bit like a replication first RNA world type scenario, and it is definitely replication first, but the actual chemistry, I'm pretty agnostic. This could be anything you really like. So, all right, so there's replicators. So there's two different kinds of fitness. There's static fitness, which is associated with function, and there's environmental fitness. So the static fitness is associated with a fundamental trade-off in chemical systems, and that is molecules that are very functional, they fold well, are hard to copy, and molecules that are easy to copy tend to not fold very well and are not very stable. So in this system, there's two ways to be very fit. You can either be very stable by being all blues, or you can be very easy to copy by being all purple. The fact that it's all one and all the other is to, 1, show that trade-off, and 2, to be very rare in the system. You expect that functionally fit sequences are rare in the scheme of all possible sequences. And then there's all these other ones that are pretty much easy to make, and they are a little bit stable, and they get a little bit of a replication enhancement, but they're not very good at either. All right. Oh, and then the dynamic aspect is your replication rate is coupled to the resources available in the environment. So for example, if you're this blue one, and there's just a bunch of purples out in the environment, your replication rate is suppressed, and the purple one's replication rate is enhanced. All right, and so we do this, we run it all together, and we get sort of 2 stable equilibrium that I've arbitrarily decided to call NonLife and life. And they have these properties. I don't think replication defines life, as I said earlier, but it's not just replication, it's selection on functional fitness that I really think is the motivating factor behind calling it life. So I'm just going to talk about these 2 different phases really fast. So if you just look at all the different length sequences, in the non-life, sequence production is dominated by polymerization. So you get this exponential decay with a little bit of a modification here because it's constrained by resources. So this is the length. So like during non-life, we say, okay, length 3, what fraction of the system mass is length 3? And it's this. And then for non-life, we do the exact same thing. You see a very different story because everything's tied up in replicators. Right? So length 7 was the minimum length to replicate, and all the mass is shifted there. You're resource limited. There's very little mass left to continue replication because it's all tied up here. And then you get the exponential decay from dimers again. Okay. So then I said functional selection takes hold in the life phase. So this is a slightly different plot. If anybody was at my talk at AbGradCon, this is a little bit different. So what I did here is, again, you have all the different length scales, 1 through 7. And on top is non-life, and on bottom is life. So the solid purple is the pure purple sequence, and the solid blue is the pure blue sequence, right? And so as you see in non-life, as you go up, you get these mixed sequences dominating. So length 7 sequences, there's replicators there in non-life, but they're these sort of heterogeneous mixtures. They're not very good at anything. They were just what was easy to make, okay? But then in life, you see a very different story. The entire system has restructured because you get selection on these homogeneous sequences. So length 7, it's about 70% of the length 7 sequences are the very stable ones. So they just sit there, they're stable, they're replicating, and they're using up all of the ones or the blues in the system. And then the rest are mostly these homogeneous zeros that replicate very fast, but they also break apart really easily. And then the entire system is just being made by breaking these length 7 sequences. So you see these same patterns being sort of copied throughout the entire thing. If you're interested why it switches from mostly blue to mostly purple right here, we can talk about that after, or you can ask me. It's kind of interesting. All right, so then another key distinguishing feature between life and non-life, I measure with an information measure. Has anybody here ever studied any information theory? Even a little bit? No? Raise your hands. One person? Cool. Okay, so if you read anything on information theory, the first thing they introduce is Shannon information, which is largely useless. And then the second thing they introduce is mutual information, which is a little bit more useful. So mutual information, if you like math, it's right here. If you're good with pictures, this kind of makes sense. But the way to think about it is if I have 2 random variables, x and y, the mutual information between x and y is what do I learn about x given that I fix y, right? So it's a way to measure arbitrary correlations between 2 different variables. You don't have to specify a functional dependence. You don't have to specify anything. You just have to have the probability distributions. And you say, given that I know x was in this state, what do I know about the state of y? Make sense? Cool. So one way to distinguish non-life and life in this model was that if you look at the composition of the replicators and the composition of the free resources in the environment, you can say, what is the mutual information between these two? So what do I know about the replicators given that I've fixed the environment? And in the non-life phase, you see a high positive value, around 3. Depends on how you set the parameters of the model. It changes a little bit. And then in the life phase, you see that they're largely uncorrelated. It tends to 0. So this means that the replicators that exist in the non-life phase are completely determined by their environment. That if you fix the environment, you know a lot about the replicators that exist, and you know about their composition. Whereas in the life phase, just because you know the environment doesn't mean you necessarily know much about the composition of the replicators, which I think is a pretty interesting sort of effect that's been caused by this selection on function. All right. So, as I said, there's a first order phase transition, and you might have predicted it. If you do any statistical physics or thermodynamics, you see these sharp discontinuities and state variables. That's a first order phase transition. So why does this happen? Well, and how does it happen? So the transition happens when the environments available, or the resources available in the environment, match the composition of replicators. So what this plot is showing is the relative difference between the composition of the environment and the free resources. And it's the frequency of the transition actually happening. So this is for 256 different runs, and I said, okay, when the transition happens, what was the relative difference between the number of ones over the total mass in replicators and the number of ones over the total mass in the environment? And you see that almost 60% of them happen when they exactly match, and then it's a pretty nice Gaussian centered around there. So one thing that's interesting about this transition is that you might expect that the very fast replicators would drive the system into this sort of new state where replication is dominating everything, or that the very stable ones would get formed, and then eventually those would build up enough of them to drive the transition. But what actually happens is because you have to match the environment, it's the very unfit, the easy to make replicators that end up causing it. So here, these are like 3-4, 4-3, even splits between purple and blue. And then here is 5-2, 2-5, and then there's a brief 6-1, 1-6. And then eventually at the end, you get the very stable ones selected. So this means that if you were to observe a transition from non-life to life, if you like alternative, prebiotic chemistries, this is exactly that. This is saying that the things which nucleate the transition into a living state are not going to be those that are ultimately selected at the end. The transition is associated with a massive explosion of diversity. So here I've plotted the total number of explored sequences on top as a function of time. And the transition happens right here. As you can see, there's this huge discontinuity. The exploration rate for exploring new sequences, this would be like speciation rate, goes up by 2 orders of magnitude during the transition, and it's higher after the transition than before. All right. But also associated with this transition is a mass extinction event, because the entire system gets restructured. So if we start here, so here I've plotted the formation versus degradation rate in the total system and the mutual information, right? So if we start stable formation degradation here with high mutual information, this is the non-life state at steady state right up here. And then it's going to eventually end up over here with the 1 value of formation to degradation. If you have anything other than 1, the system's unstable, so it has to end there. And so as you see, the mutual information starts going down. Everything's getting ripped apart faster than it's being made. Anything below 1 means for everything you're making, you're destroying more than that thing. Hits this bottom, and then eventually stabilizes by finding the functionally fit sequences. So yeah, in summary, functional selection leads to an observable decoupling of replicators from their environment, and this by driving a restructuring of that environment. This restructuring would have been associated with an explosion of diversity and a mass extinction event, and the replicators which came out of that would not have been the ones that nucleated the transition. And for the sake of time, I'll just skip these future directions. If you're interested in why simple replicators are not the right logical architecture for life, you can ask me about that later. It's pretty cool. And yeah, that's it. Thanks to all these people, especially my advisor, Sarah Walker. She's super rad, and she's been very helpful in all this. And that's it. I'll take any questions.
Okay, we have time for one quick question.
You already have the mic.
So, can you say anything about the species that nucleate the emergence of life from the context of the things that are life?
So in this model, they would have been made out of the same basic building blocks is all it really says. But they would have been structured completely differently. So the sequence composition and the actual sequence play 2 different roles in the way the fitness landscape is instantiated. So depending on how you want to interpret the chemistry or match it to some kind of toy system, there are some things you might be able to say, but it's really sort of touchy. But they would have been reflective of the initial composition of the system. So they wouldn't have been outliers in the scheme of all possible sort of compositions.
As super chair, I'm granting myself extra time to ask a question. This was super cool, so I want to know what the future direction is. Just a 30-second,
yeah.
Where are you going next?
Yeah, so when I made these slides, actually, I had a different idea. This project came out of some other ideas that I thought this was going to be like the easy step, and then like, okay, cool, we'll actually be able to ask a question, and then all this phase transition stuff happened, and I was like, whoa, I didn't understand that or expect that. So the future direction is I'm looking at different evolvable life histories, or sort of, yeah, life histories. So, if your prebiotic chemistry discovers a polymerase before it discovers like something that can recycle things, or a synthase, or something that makes components that you need, how does that enhance or slow down the evolvability, and sort of how does that change how constrained your rate constants basically need to be in that system? But I'm also interested in, so von Neumann's got this great idea about what things need to do to be able to make copies of themselves. And it needs a specific logical architecture, and I can point you to some references, but basically you need a replicator and a vehicle. And all of these replicator models that have ever been made ignore that, and they just say, oh, well, we just have a replicator, but you compress a lot of biological function, and you introduce a lot of logical paradoxes if you try to do it that way. So I'm interested in that.
Okay, thank you, Cole, for such a strong finish for us.
Thanks. letting me